So in the spectroscope lab, as far as the calculations go, you're asked to calculate the frequency and the energy. Okay? Now there are a couple of ways you can do this. I think the easiest way is to first calculate the frequency. And what I would do is I would create a table, one where you calculate the frequency, one where you calculate the energy. Now the equation we're going to use to calculate frequency is that one. So to solve for frequency, we got to do some algebra. So we have to divide by the wavelength. Now from page 1, you have the wavelengths there. You might have a wavelength of 4.10. Now this is why it's always important to write units, because the units on that was nanometers. So you need to convert that to meters. So to convert that to meters, we would multiply it by 1 times 10 to the negative 7th. So all of those wavelengths on the front page should actually be times 10 to the negative 7th in meters. Okay? So every of the numbers you recorded on the front page is actually times 10 to the negative 7th in meters. So then we take the speed of light, divide it by the wavelength in meters, and that'll give you your frequency. And the units on that are hertz. A hertz is also an inverse second. Now once you have the frequency, then you can calculate the energy using this equation. Okay? So H is Planck's constant. And it doesn't matter which Planck's constant you want to use. I'm just going to use the bigger one, 3.99 times 10 to the negative 13th kilojoules times seconds per mole. I like using that Planck's constant because it gives me a bigger answer. But you could use the other one. So I take that times my frequency so then I end up with an energy of 292 kilojoules per mole. So that's the calculations you do for the spectroscope lab, and then all you got to do is redo it each time with your new wavelength, because you should have at least 7 wavelengths on the front of your lab, and then you redo the calculation each time for each new wavelength.